Hello and welcome. I'm Maurizio Cimadamore and I work for the compiler team in Oracle. You may have seen my name associated with many of the language features we have been able to ship over the last few years, so lambda expression, local variable type inference more recently. Today I'm not going to talk about language at all. I'm going to talk about something completely different, something that I've been working on for the last year or so and I'm very excited about. It's called Project Panama. And as we have learned from Mark's talk, Project Panama is all about bringing native library closer to Java. This is a word from our sponsors. Of course, everything I say should be taken with a pinch of salt. Of course, Java has a way to interoperate with native libraries, and that way is called JNI, Java Native Interface. Quick show of hand, how many of you have actually used JNI? Okay. Quite a bit of people, so you know what I'm talking about here. So JNI allows you to declare a native method, and to do that you just declare a method as native. You put the native keyword on it, and that is like an abstract method. It's something that doesn't have a body, a method that doesn't have a body, and it's up to the VM to find the implementation for that method, and the implementation will be defined in terms of some symbol available in some native library that is loaded within the VM. Typically, developers reach out for native method in three situations. First, when they have to interoperate with some legacy code that cannot be rewritten in Java. Second is when they need to access functionalities that are not available within the JDK. And third, to increase performances. And about these last 2 points, I think we are going to talk a little bit more in the next few slides. The relationship between JNI and Java has always been a little bit ambivalent. And as you can see, I mean, I cannot be a Devoxx without quoting something from Joshua Block, right? So in Effective Java 2nd edition, there is this chapter, this item, 54, that says, use native methods judiciously. What does that mean? Well, there is a lot of misconception about JNI. One of them is that JNI is fast. In fact, it is not fast. And if you believe that JNI is going to make your application faster, more often than not, you're wrong. In fact, JNI defies a lot of the optimization that the just-in-time compiler can do for you. A second misconception is that there are a lot of functionalities for which you need to go native, while in reality the JDK API is so rich that most of the time you can just remain within the realm of the JDK and not touch any Java code at all. As we shall see, this is kind of changing rapidly. So around 2008, the conception was that, well, JDK is big enough. It has a lot of functionalities. We were just about to add NIO too. So we could do things such as file watchers and things that we were only capable of doing with native code before. And the just-in-time compiler was getting better and better. So you just updated the JDK and your application just ran better. So native method, there were not a lot of room for them. They were just a tool aimed at experts, and JDK developers, such as myself, were one of those experts that were often using these tools. Other than that, not a lot of people used native methods. Well, this all started to change with machine learning, right? Machine learning started to put a lot of pressure into trying to perform numeric computation as fast and as quickly as possible, because all the core of machine learning is essentially linear algebra computation, matrix computation, and all that stuff is good news, is easily parallelizable. In fact, those problems are called embarrassingly parallel. But bad news, the CPU doesn't provide us a lot of cores, does it? And that's why the machine learning folks turn into GPUs. GPUs have a lot of cores, and surprised, their cores are actually optimized to perform numeric computation. So they seem like the perfect tool for machine learning workflows. And it's not a surprise that the most popular machine learning frameworks adopt and take advantage of the GPU acceleration that is made available by recent GPU cards. The problem is that all those frameworks at some point need to access some native library in order to take advantage of this acceleration. So basically we are starting to see a shift. Previously we said to developers, well, you should try to write your application in Java, and you were kind of considered dirty if your application wasn't 100% Java. Now, today, things are a little bit different. And even Joshua updated this book. Well, the item number has changed from 54 to 66, but more importantly, the text of the book has been changed and updated to say that, well, if you really care about really fast numeric computation, there are libraries available out there. So maybe in those cases, it could be justified for you to use a native methods. The core of the issue here is that there are cases where you just have to go native. Maybe you want to do some off-CPU computing. Maybe you want to do deep learning. Maybe you want to use a graphic library, and graphic libraries are all native. Or maybe you just want to use a popular open source library, such as OpenSSL, which in many cases uses a replacement of the SSL library provided by the JDK. In all these cases, you need to access some native library. And the best thing that a platform and a language can do in those cases is really to try to lower the activation energy that allows people to access native libraries. And what is the story that Java has to do this? Well, JNI. JNI is, of course, a very general tool. It allows a very rich interoperability between Java and native code, but as we shall see, it has its own limits. So this is like the very first example that you will try to write using JNI. So we want to call the getPid system call using JNI. And well, if we play by JNI rules, then we declare a class. I call it getPid. We put a native methods inside the class. And then we just create the class and call the method. That sounds easy, doesn't it? Except it's not. So if we look at the workflow, we start with the getPid Java class, and we compile it with javac, but we have to provide an extra flag called -h. It used to be called java h. It was a separate tool. Now it's been merged into javac. And what this does, not only generate the class file for your getPid class, but it also generates an header file. What do you do with the header file? Well, the header file contains the entry point that the VM looks for whenever you call your native method. So you need to implement this header. You need to provide your own native implementation. And then you have to compile everything with your favorite compiler of choice, GCC, Clang, Visual Studio, and produce a shared library. So that's kind of the workflow, and that's the code that is involved in order to get the getPid example working. Not only we had to make changes to the Java code, because if you notice on the left column, we had to add the system load library call in order to load our system library to make sure that the VM can actually see this library. But there's also a blob of header file that has been generated by javac in the middle, and there's a bit of C code that we had to write on the right. And this is all a very simple example. I'm not even passing arguments or anything. Of course, there are a lot of things that can go wrong here. If the library that I'm trying to call from the C implementation is updated, then maybe I have to change the C implementation, and that means that maybe I will have also to change the Java implementation and regenerate the headers. A lot of things can go out of sync here. A lot of things that the developer has to worry about. And if we zoom in into the native implementation, we see that, well, actually JNI is doing a lot more work than we think it does, because in fact it's passing an extra parameter called JNIenv, and this is effectively a pointer to the entire VM. So by using this JNIenv, we can perform any kind of Java-related task, such as allocating objects, arrays, accessing fields, methods, even throw exceptions. And if we look even farther, well, JNI, this is an instance method. I'm calling an instance method. JNI dutifully pass the receiver object to the native method that I'm going to implement. And if we think about it, the garbage collector moves object around all the time. So how the heck is the native code supposed to be able to refer to objects in a stable way? Well, JNI has to do some heavy lifting here. It has to create the so-called JNI handles that are basically an extra indirections to the object that are actively maintained by the GC. And that's how native code can access safely to objects. Of course, this adds complexity to the VM implementation. And that means that things that should be easy, in reality, they are not. And if you are brave enough and you want to look into some assembly, there is a great talk on YouTube called Why is JNI Slow that shows you all the assembly instructions that the VM has to output in order to safely call into a native method. And there's quite a lot going on. So let's try to evaluate JNI from the perspective of a user that only wants to be able to access a native library. JNI is certainly a very good framework in the sense that it allows bidirectional interaction between Java and native code. Not only I can call native code from Java, but I can also call Java back from native code. And that's a plus. We want to keep that moving forward. But there are a lot of things that are less convincing. So, for example, there is no support whatsoever for modeling off-heap data. And that's a pain point. Users typically resort to APIs such as unsafe or byte buffer. And actually, did some archaeology on this, and in the very first version of JNI 1.0, that version allowed people to model native structs as Java objects. And of course, that got binned in version 1.1 because it was too dependent on whatever the VM choose to do for implementing Java objects. So as of today, there's no support for modeling native structs in JNI. As we have seen, the just-in-time compiler needs to treat JNI code as a black box. It doesn't know whether it can create objects or throw exceptions, so it has to put safeguards all around it. And the ugly part is really that the workflow for getting anything to work with JNI is very complex. And the complexity in the VM itself is also very high. We have added features over time, such as critical JNI sections. So pieces of JNI code that are trusted by the VM, in which we can say, okay, I trust you not to move this object around, and I'm doing this logic over here, and basically to avoid some of the overhead that is associated with JNI. And this stuff adds complexity to the VM implementation. So we want a new way to interact with native code, and this new way, we think it's Panama. The goal of Panama is really to allow Java developers to use native libraries that are available and that are easily accessible in other languages. So if there is a library out there that people find useful, it should be easily accessible from Java. The way we do that is by stepping back and basically not rely on native methods, and instead model everything, structs, headers, with annotated interfaces. So we are going to use interfaces a lot. We are going to put metadata on interfaces in order to capture the essence of the native data that we are going to model. And then we are going to generate implementation on the fly by using a runtime component that in Panama is called the binder. So the binder takes an interface with some metadata, generates an implementation, and then you can start just using it. And since this implementation is generated by JDK, it can be trusted by the VM. And that's where the performance benefit comes off. Panama also provides a rich API to model off-heap data. So keep an eye for abstractions such as layout, pointer, array, and scopes. And the result, hopefully, should be that we need no more native methods. This is getPid rewritten by using the Panama machinery. So as we can see, I have an interface called getPid. It has a method called getPid, again, that returns an int. But I have to put some metadata in there to tell the binder what is the real native signature of this method. So in this case, the method takes nothing and returns an i32, which is really an int. I don't want to dive too much into the details of this little DSL that we invented in order to model native signatures, but suffice to know that we can express whatever piece of native type you can find into an header with this little DSL. Once I have the interface, of course there has to be a mapping between the symbols that are defined in the header and the members of the interface. Once I have the interface, I can bind it using a method in the Panama API, and then I get back a a regular Java object, I can call methods on it, and that's it. There's no native code involved. So basically, what used to be a very convoluted workflow with a lot of steps that even went through basically calling a platform compiler, now it just reduced to this, really. You write your Java code, it has some annotation, you compile it, you get a class, and then you run it. Of course, if you want to do more than just calling getPid, you are going to need more GUIs. And one of the first things that are needed when interacting with native code is some API to model pointers. Almost any framework that I've seen that are doing some kind of interoperability with native has some pointer class of some sort. So Panama is no exception, and it has a pointer interface. This pointer interface is generic, so on X, and it really encodes three different information. It has an address, which is basically where the pointer is pointing to. It has a layout, which is an API that in Panama allows to describe the shape of the memory that we are pointing into, so whether we are pointing into 64 bits or an array or a struct. And it has a Java carrier. Why do we need a Java carrier? Because whenever we need to do a dereference operation, when we need to get bits out of the pointer or to put things into the memory region pointed to by the pointer, we need to tell which Java type we want to use. So there's always a Java carrier associated with pointers. There's also a fourth hidden information, which is the scope. So all the pointers come from a given scope. And that acts as an ownership model, really. So you can only dereference pointer and use pointers if the owning scope is still alive. If you already close the owning scope, then every operation on the pointer will throw an exception. So that's how we achieve safety with Panama pointers. Arrays are really something that is derived from pointers, so we can encode an array as a pointer plus some length information. So that's not really very interesting, but we can model arrays in this way. So this is how we access off-heap data. I changed my example. Now we are going to use the string length method because that's more interesting. It takes a pointer to car. So in order to allocate, we need to create a scope. And this is typically done in Panama using a try with resource construct because scope is, surprise, surprise, an auto-closable class. So if we allocate a scope with the try with resources, then basically the block of code denoted by the try with resources is the piece of code in which it's safe to dereference and operate on those pointers. Once we have a scope, we can ask the scope to do some allocations. We were lucky, there is just a method to allocate a C string, a zero terminated C string, and get a pointer to it. So we can call the allocate C string method and then pass the pointer to the string length library. And that just works. Of course, there are more advanced use cases. In native code, you will find things such as structs, callbacks, and my goal here is not to show all the gory details about all this, how this stuff is implemented, but I want to kind of give you an idea that even without native methods, we can get all this stuff working. So this is an example with structs. It's the same example that Mark showed earlier. Basically, we have the time spec struct, which is, we have the clock get time function, and that takes a pointer to a time spec struct. The time spec struct is modeled as an interface. This interface has an annotation called native struct, which again takes some DSL describing what is the layout, that is the machine-dependent layout for that particular struct. Once we have an interface modeling a struct, then we can, again, through a scope, allocate the struct, and then we can just use it as a normal POJO. So we can call accessor method on it, we can set fields, we can get fields, and we can pass it to function taking the struct, and everything works. And this is off-heap data, so all the time we are interacting with memory that is not managed by the garbage collector. Another important case in native code is to be able to model callbacks. The prime example of that is qsort. So whenever we want to write an algorithm and we want it to be able to work on different data types, A common trick is basically to delegate all the data type dependent logic to some callback function, and qsort does exactly that. So it asks the user how the element should be compared. And so we need to be able to support this kind of idioms in Panama as well. And the way we do that, again, is through interfaces. So there is an interface here called comp, and is annotated with an annotation called native callback. Again, that takes some metadata that describes what is the native signature associated with the callback. And if we have a scope, we can allocate a callback. Now, this allocation is a little bit magic because we can pass a lambda expression that represents the body of my callback, but behind the curtain, the VM will also do some code spinning here because it will have to generate an entry point that it can then pass as a function pointer to the native function. So all this happens magically, and when the scope is closed, the code snippets that the VM has generated disappears. And with this technique, we are able to do callbacks and support them in Panama. So we've seen quite a lot. So let's try to recap a little bit. We've been able to model everything using just interfaces plus some annotations, no native methods at all. So the workflow, the resulting workflow is a lot simpler than the one that we've seen with JNI. There are still things, though, that leave me a little bit dissatisfied. For example, if we look at this example, all the stuff in blue, like the stuff inside the annotations, contains a lot of machine-dependent details. So I have to know that qsort is taking like U64, so a pointer that is encoded as a 64 bits, unsigned, and then it returns some I32. How am I supposed to know all this information? What if I have to distribute this code on all platforms? And there's quite a lot of details that the user will have to know. And of course, this process doesn't scale if I want to port entire libraries. Let's consider TensorFlow, which is a real case. It has an header file, and this header file has 161 functions, 23 structs, 50 constants, and 2 callbacks. Am I supposed to know all the machine-dependent representation for all this function? This can get ugly pretty quickly. So I think we need a way to do it better, and the way to do it better in Panama is to use tooling. So there is a tool called jextract, and jextract is simply a way for us to point the tool to the header that we are interested in, and jextract will do the rest. It will parse the header, will find all the dependency, and generate a bunch of class files bundled in a jar. Jextract is built on top of the Clang parser API, so it's a very robust API that is well capable of handling all the C and C++ code out there. And of course, the bundle that jextract generated are platform dependent. The annotations that are generated by jextract will be machine dependent. They will depend on the machine that you're running on. While jextract is still a prototype, of course, we are in a very early stage, we have some success at extracting real-world libraries. So we have been able to extract libraries such as TensorFlow, BLAST, LAPACK for matrix computation, OpenGL, and I'll show you a demo about that, and Python. So while this is still kind of a toy, well, it's a pretty serious toy. You can do some serious stuff with it. So this is the workflow we had with Panama. So you still have to write the getPit Java file, you compile it, you get a class, and that's it. But we have seen writing this Java file is not easy because it contains a lot of platform-dependent annotations. So jextract helps us because, well, it just makes the task of writing the getPit Java class redundant. We can just point jextract at the header we want, in this case unistd.h, and jextract will generate a bundle, unistd.jar. And what's in this bundle? Well, there's a bunch of classes, among which unistd.class. And if we zoom in, well, we'll find our old getPid method that we want to call. So instead of writing this in Panama, what you really do is you run jextract on the header file you want, and then you just import the results. So there's no declaration that you really have to write. You can just rely on jextract to do the right thing. So before looking at performances, I wanted to show a little demo of an OpenGL example. Let me see if I can mirror the display. Magic incantation, yeah. So this is disclaimer, I'm not an OpenGL expert by any means. I basically put this together by looking at various tutorials and kind of stitching them back and converting them using the Panama API. The goal was to draw a teapot and to put a texture on it. And of course, in OpenGL, as soon as you start, you learn that you need at least 2 libraries. You need, yes, the OpenGL library, but you also need the glut library, which is used to create the window, initialize the display, and everything. So here you can see that I'm binding, in fact, those 2 libraries. I'm binding the GL library, and I'm binding the glut library. Then if we scroll down, we can see that there's a lot of initialization code here. I'm allocating a bunch of off-heap arrays to essentially initialize the Lightning model of OpenGL. So there are a bunch of calls here that are all related to Lightning. And if we scroll down farther, that's the code that set up the texture. And texture is kind of interesting because in OpenGL, if you read all the tutorials, they say, well, in order to set up a texture, you need to have an array of pixels. And to get the array of pixels given an image, you have to load the image using a third-party library. But hey, here we are in Java. We have a perfectly good image reader API, image.io, and we can just use that to read the array of pixels. Then we can create an array of heap, and then we can call the function that sets up the texture for us. If we scroll further down, we have a bunch of methods which are really used as callbacks. It's probably clearer if we just look at the main method. The main method creates one of those scopes, abstraction, and then it starts to allocate basically all the display context. So it creates a window, it creates one of these teapot objects, it sets up the display function and the idle function. And the display function is really where the action happens. The display function is what draws the teapot. There is, luckily, a primitive available for doing that. It rotates the matrix a little bit, you swap the buffers, and that's it. And whenever the system is idle, we will be rotating the teapot a little bit. So this is all straightforward OpenGL code. I guess anybody who's familiar with the OpenGL API will find this remotely similar to what they've been doing. And let's try to run it, see what happens. Yeah, that seems pretty smooth. So to give you an idea of the scale that's involved, let's try to let IntelliJ decompile one of those libraries. So let's take GL, right? It will take actually a few seconds, which is an indication that it's pretty big. So let's try to scroll all the way to the bottom of this thing. As you can see, there are like 12,000 lines of decompiled code in here. So it should be evident that it's not possible for a human to write all this code. And what happens if the OpenGL library changes? Then you have to tweak some of these functions. And that's why maintaining JNI bindings is so hard, because they are huge. They contain a lot of information, and the process is error prone. If you have a tool like jextract, you can just generate all this stuff in 3 seconds, and that's it. So I guess we can go back to the slides. Okay, so when it comes to performances, I guess our goal here is first, not to do anything fancy. We are starting with JNI, so we should at least be able to match whatever performances JNI was able to obtain. Our reasoning here is that if we provide something that is more usable than JNI, but it kind of provides the same performances, well, it should still be a pretty good deal for people to start using and play with. And I'm happy to show that we managed to fulfill that promise. And in fact, this is a performance graph. It shows the throughput of a get-pid call, and the bar on the right is Panama, the bar on the left is JNI, and we can see that Panama is marginally faster than JNI. Nothing worth writing home about, but still, for me, the important fact is that the bar kind of looks similar. Of course, this is not our objective. Our final objective is to completely overhaul the performance model provided by JNI by getting rid of all these inefficiencies that lie within JNI calling conventions. And Vladimir Ivanov and I have already started looking at an alternate backend for supporting native invocation using Panama. And we call this backend link to native. And this is what the performance graph looks like. So you can see the blue bar is link to native. And the other two bars are Panama versus JNI, vanilla Panama plus JNI. And you can see there's an order of magnitude of almost 4x between regular JNI and link to native. So that's kind of the performance boost that we are after with Panama. So it's not only about usability, it's also about trying to remove all the inefficiency in the JNI protocol to get better performances. Of course, with every piece of good news, there's also bad news, so let's get on with it. This is QSort. We can see that the performances for QSort are promising in the sense that Panama is still going a little bit faster than JNI. This is essentially a QSort implementation that's doing an up call into Java in order to compare the elements. Now, what if we didn't do the up call to Java to compare the elements? What if the callback was written entirely in native code? Well, in that case, that's what it looks like. So if you remain native to do the comparison, you get code that is 10x faster than whatever JNI or Panama are able to provide. Well, this is not entirely accidental. The code path for doing up calls in JNI are absolutely not optimized. JNI is kind of optimized for doing down calls, but is not optimized at all for doing up calls. So Vladimir Ivanov and I are actively working to essentially do the reverse trick of link to native for up calls. And while I don't fully expect that we will be able to reach the 10x performance improvement, I think we should be able to get pretty close to that. And that should be a very good news. I think the more we blur the boundary between Java programming and native programming, the more stuff like this is gonna bite. Because if you want to pass Java code as data to native function, you want it also to perform. You can't just pay a 10x performance footprint every time you have to do an up call. So it is pretty crucial that we improve on this number. So with Panama, we have seen that without native methods, we are able to model all the essence of the concepts in native programming. We are able to point a tool called jextract and get a bundle of annotated interfaces back that we can just use without any extra step in the middle. It is a safer alternative to JNI. Because there is a lot of APIs, such as the scope API, that allows you to keep your pointers in check. So you get an exception whenever you're trying to use a pointer and you are outside the scope that owns the pointer. And as we have seen, the room for performance improvement is huge. All this area is not very explored, but there's a lot of inefficiencies that we can get rid if we know that the implementation that do the down call or the up calls are something that the JDK can trust. And if you think about it, all the concepts that we have seen so far are very general. The definitions of the native signatures, they are defined not in terms of C concepts, they are just defined in terms of signed integer, unsigned integer, 32 bits, 64 bits. They don't contain any detail about the target native language, which means we can reuse them. We can reuse them even for something that has nothing to do with interop with native libraries. We can, for example, use the Panama layout definitions for describing message protocols. You can describe a message, a protobuf message using the Panama layout definition and allocate a protobuf instance of heap if you wanted. So all these tools are very general, and we hope that people will use them for more than just for C interop. Where we are today is, I'm glad to announce, we managed to ship the first early access binary. So if you have a Linux or a Mac x64 bits, you should be able to download one of those binaries and start playing with jextract and the Panama binder. This supports essentially all the C features. We even recently added support for x87 complex numbers and corners like this. So I would say it's a pretty mature support for C feature. Jextract needs a little bit of work. We need to improve usability of the jextract tool. And this is all based on the conservative JNI backend that I shown you earlier. So this is not using the link to native approach because that's not stable yet, but we plan to make it available very soon. Where do we need to go in the future? Well, there's a lot of topics that we need to explore from here. If we want to ever reach to use cases such as C++, we need to make our extraction story a little bit more nuanced. It's not just about having classes with annotations, it's also about embedding snippets of native code inside the generated artifacts. Because some features in C++ can only be implemented if you have support from the native compiler. If you have an overloaded method, or if you have an inline function, there's no way you can understand that without the help of some compiler. So it is very likely that in the future you will see jar files that contain not only classes, but also some shared library. We have to explore the direction of enhancing our layout description because, for example, when you start to model message protocol schemas, it's very common for those schemas to have variable size things in them. So, for example, you have a string and the string has a length field and then it has a sequence of bytes. And that means that the layout is not fixed. It can vary. It varies depending on the value of that particular field. So we need to enhance our layout description in order to scale for that particular use case. We have to work more on supporting Windows, and we are making big progress on that, thanks also to the help from the community. And we need to start using our own medicine and use Panama within the JDK. We already had very good examples where just by switching from JNI code to Panama, without any fancy backend, we were able to improve over the performances because a lot of the code that was previously expressed in terms of native code within some obscure piece of C JNI code is now expressible in terms of the Panama OFIP API. And since it's now Java code, the just-in-time compiler can optimize it. And more often than not, it does a better job at optimizing that code than the C compiler will. And you can keep track of the progress on the Panama foreign branch, which is all where all the action related to jextract and the binder happens. And you can join our mailing list and report your feedback there. This is the end of my talk. I think we have plenty of time for answers and questions, hopefully.
JNI and JNA, you can have multiple implementations, like one for Windows and one for Linux. How does Panama do this? If the implementation is completely different, but the interface is the same.
What do you mean by implementation? Sorry, basically the question is how do we handle cases where we want to have the same interface, but under the hood implementation is different for different operating system?
Yes.
Yeah. Well, if the layout is the same, like if your struct is taking a couple of 64-bit fields, then you can maintain the same interface. Of course, if there are more profound differences, you can't. And there's no way around it. At some point, you're going to encounter some issues if you try to abstract over a difference that is that important. So
You need your own wrapper around it then.
Well, you need to load the version of the interface that is more relevant to your platform. We have been talking internally about having some kind of multi-platform jar, something that you can use as a delivery mechanism for distributing this kind of interfaces that are tied to the particular platform that you are running on. So this is an area where we need some more exploration. It is also possible that maybe Panama will be used by, there are tools out there that already solve this particular problem of distributing like a Maven artifact across different platforms. There is, for example, a tool called Java CPP that is doing exactly this. So it's packaging up native libraries and distributing them over Maven. And they have a library loader that tries to load the right thing at the right time. So there are ideas out there on how to do this. Yes?
How do you take into account that when you pass objects from Java land to the native land, how does the garbage collector know that this object is now used in your native code and not free the memory while it's in use in the native code? Because it's essentially leaving the JVM into native land, and you somehow need a mechanism to tell the JVM, I would assume, that this object is now in use by native code, and you also need a mechanism, I assume, to tell that you can free it now.
So the question was, how can Panama take care of basically passing Java object into native code, given that when you transition from Java to native, then you are into unmanaged code and you don't know how long you have to keep that object alive for how long? Well, Panama answer is not to pass any object to those methods. So you can't pass anything.
So if I have a native interface, say a callback that accepts a void pointer for user data, arbitrary user data, I cannot use a Java object as arbitrary user data.
No.
That's quite bad, no?
Mm,
If the C header file expects me to provide random user data, and that user data, that void pointer, is implemented by me in Java code, then I cannot use that library in Panama.
I think we can probably take that offline. I'm not sure I understand the particular example. Yeah. Yep.
Yes, but you still have the use case with the void pointer and the user data, right? Okay, yeah, let's discuss after.
Okay. Thank you.